And now I'd like to talk about intersymbol interference, also known sometimes as the patterning effect. And in particular, I want to talk about how intersymbol interference comes out of filtering effects. So we said that our channel is practically always bandwidth limited. Any components that I use have a finite bandwidth. They'll only support signals over a finite bandwidth. And the signal, of course, is always time limited, so it's never bandwidth limited. That means that I'm always trying to force through a signal, which is essentially of infinite bandwidth, through a channel which is always of finite bandwidth, which means that I should, because of this, lead to pulse broadening. Of course, it's all a question of degree. To which degree will I get pulse broadening? First of all, I'm going to show you why it is that this gives you pulse broadening, and then I'll try and show you how to quantify how much pulse broadening you get from this effect. So let's take a really simple example. In this example, I'm plotting here first the frequency domain, and in blue is my signal. So I have a signal with a bandwidth. I think this actually used the null-to-null bandwidth when I was doing the simulations. And I put this signal through a channel with rectangular frequency response. The bandwidth of the frequency response is 10 times the bandwidth of the signal. And this signal, you can see it's a sinc function, which means if I look in the time domain, in red I have the original rectangular pulse which is transmitted. It goes through this channel which has 10 times the ostensible bandwidth of my signal. And in blue we see the output of the filtering process, and we can see some small ringing at the edges of the signal. When the signal goes to 0, in fact it doesn't go to 0 at the output, there's some blue ringing around 0 that we can see. And this is sort of a stretching of the original pulse, so this time duration is greater. Now what happens is I try to squeeze this signal into a smaller channel. So now I'm going to show you simulations where I just put the signal through a channel with comparable bandwidth. Now when the two bandwidths are about equal, you can see that I have much more ringing coming out of the filter, and that now the time duration of the pulse is wider. There's ringing off in the 0. And of course if I try and make the bandwidth channel smaller, what I get is more spreading. In fact, quite a bit more spreading in the time domain. And if I try to get a very ridiculously small channel that is 1/10 the bandwidth of the original signal, I have immense amount of spreading. So this is why channel effects alone can lead to dispersion of the original pulse, so that the pulse is no longer confined to a limited time duration. And of course this would be fine if I sent bits in isolation, but of course I send a train of bits when I communicate, which means that one pulse will not have finished due to this spreading in the time domain before the next bit is transmitted. And so what is received at the receiver is the accumulation of all of these pulses, some overlapping. And so on the far right, on the bottom, we see the received signal, which looks very different from the rectangular pulses which were sent on the left. And in fact, if we set a threshold at the midpoint of the 0 and 1 levels on the received signal, we can see that sometimes we could make an error. If you notice, the dashed lines indicate the sampling point of the receiver. So at the sampling point, which would normally be at the widest point of the eye opening, we could, even though we had a 0, mistake it for a 1 if the spreading was severe enough. So this is what we call the intersymbol interference effect. And again, as we saw in the example, the level of the intersymbol interference is directly related to the relative bandwidth of the signal in the channel. I just wanted to mention that, of course, we also have in optical communications other sources of pulse spreading. We can get intersymbol interference from dispersion in transmitting signals, pulses over an optical fiber. Same effect on bit error rate. However, I'm going to be talking about ways of combating intersymbol interference, how to avoid intersymbol interference. And of course, these methods are for intersymbol interference originating from filtering effects, and they wouldn't. We have other methods of combating chromatic dispersion in a fiber, but now I'm talking about filtering effects.